All right, so what we're going to look at is chapter 14, which is about oscillations. And we're going to start with problem 19. So that's about energy in simple harmonic motion. Problem 19 says, when the displacement of a mass on a spring is 1/2 the amplitude, so 1/2 A, what fraction of the mechanical energy is kinetic energy and what fraction is potential energy? Okay, so let me straighten my papers up here and get all situated. Now, and I'm going to write in Sharpie so that you guys can see this. Okay. All right. So it wants to know, this is problem 19. All right. It wants to know when X is equal to 1/2 A. So I'm at 1/2 the amplitude of the motion. So I'm halfway back to equilibrium. Okay. Now, it wants to know what fraction is potential energy and what fraction is kinetic energy. So the total energy, remember, E is your kinetic energy plus your potential energy. And I use U for potential energy. I don't know what your other teachers used, but that's usually what I call it. Okay? All right. So the way I'm going to write this out is I know that kinetic energy is 1/2 mv squared, but I don't necessarily have to write it out like that because it just wants to know the total kinetic energy. I'm not solving for velocity or anything, so I'm going to leave it as kinetic energy. But I'm going to go ahead and write out what total energy is. And if you read your chapter, you know that the total energy of an oscillatory motion is 1/2 Ka squared. That's the definition. Oh, that's a terrible square. 1/2 Ka squared. Okay? And then plus potential K, and then plus potential energy. Potential energy is 1/2 Kx squared. Okay, that's from Hooke's law. That should be from Physics 1. Okay, so you should remember seeing that. And then we learned that the total energy of a spring system is 1/2 Ka squared. So if I know that X is equal to 1/2 A, then what I'm going to do is I'm going to put this in right here for X. Okay, so that gives me 1/2 Ka squared is equal to kinetic energy plus 1/2. Then I'm going to put in 1/2 A, and then that's all squared. So I just substituted in what they told me in the problem for A. Okay, all righty. So I'm going to bring this on down. 1/2 Ka squared plus big K is equal to 1/2. Whoops, let's get that up. 1/2. Now, if I square this, I get 1/4 A squared. All right. Now, so now what I'm going to do is I'm going to just rearrange some stuff. Now, you may say, oh, look, I can take 1/2 and 1/4 and make that 1/8. And yes, you can. But that might not be the most efficient use of your time. And I'll show you why. I want to make this term look like this term, okay? Because this is the total energy. So if I can make this look like this, then I can tell you what fraction of the total energy that is. So I'm going to come on down with this. 1/2 Ka squared is equal to kinetic energy plus. I'm just going to swap the 1/4 and the 1/2. I'm just going to flip them around like that. Oh, I left a K out. Oops. K. There we go. I left my K out. All right. So now look what I've got. I've got 1/2 Ka squared and 1/2 Ka squared there. All right. So if this was the total energy, then this thing in here is also the total energy. So now I've already got my answer. The potential energy is 1/4 of the total energy. Okay. So potential energy is 1/4 of the total energy. So that must mean the kinetic energy is the rest of it. So it's 3/4 of the total energy. Okay. So all I've done, the reason I didn't go ahead and multiply this out right here is I wanted to make it look like this total energy term. And then I could say, oh, that's just 1/4 times my total energy, and that's my fraction. So that sometimes you don't always want to multiply stuff out in these problems. You want to leave it and see if you can rearrange it a little bit. And we're going to see that show up several times. So don't get super excited about multiplying things out, okay? All right. So there's that one. Does anybody have questions on that part of that? If you have questions, just unmute yourself and ask. No? All right, we're going to move on then. Okay, so part B says, at what displacement as a fraction of A is the energy half kinetic and half potential? Okay, so there's my little blotter page that I use underneath here, because, you know, writing with Sharpie. We're going to get iPads someday. They say they ordered us some iPads, and when they come in, then this will look a lot nicer, and I won't have to be writing with a Sharpie. But right now, we don't have them, so Sharpie is what you get. All right, so says what displacement is a fraction of A is the energy half kinetic and half potential? So now this is part B. I know that I want the energy to be, it's still kinetic plus potential, but I want each one of these to be 1/2 the total energy. I want each one to be equal and 1/2. So, all right. So if I take this and I solve, I know there's a couple of different ways I can do this. All right. I know that I want the potential energy to be 1/2 the total energy. So I'm going to take advantage of that and say that, well, I know that potential energy is 1/2 kx². That's the definition of the potential energy of a spring. But I also want that to equal 1/2 the total energy. All right. So let me look at these two pieces right here. So I've got 1/2 kx² is equal to 1/2. The total energy is just 1/2 Ka², as we've already seen. All right. So I just substituted in this for the total energy. Again, I can get excited and multiply those together, but I kind of don't want to do that because I can do like that and cancel those out. I can also cancel the K out. So I'm left with x² is equal to 1/2 A². And then all I need to do is take the square root of both sides. So if I do that, I get x is equal to 1 over the square root of 2, or square root of 1/2, and then the A is out by itself because it was squared. Okay, so if you want to be really super fancy with math, you can say that's 1 over the square root of 2 times A. So the position where I have half potential and half kinetic, in other words, they're equal to each other, is when x is equal to 1 over the square root of 2 times A, which is like 0.7 centimeters or something like that. Okay. All right. So that means I just have to remember what the definition of spring potential energy is from Physics 1, and then use my new definition of total energy of a block spring system here in terms of amplitude. All right. Anybody got any questions about that one? Is that okay? Okay. All right. So for our next one, I want to look at problem 25. Okay. So problem 25 says a 200-gram mass is attached to a horizontal spring and it oscillates at a frequency of 2 hertz. At one instance, the mass is at 5, or at one instant, excuse me, the mass is at 5 centimeters and it has a velocity of negative 30 centimeters per second. And then you want to determine a bunch of things. Okay. All right. Now, one thing that I will say, and I didn't have this question on the lab, make sure you remember we work in MKS units, so meters, kilograms, seconds. You have to make sure that you convert everything to meters before you do any math, and kilograms and seconds, all right? So this book loves to not be in those units. So the first thing that you always should do is make sure you're in the right units before you try to work a problem. So this is problem 25. Oops, 25, turn that over, there we go, 25. And it says I've got a 200 gram mass. So I'm just going to immediately make that 0.2 kilograms before I do anything else. And it is a 50 centimeter, oh, excuse me, there we go. It is at a frequency of 2 hertz, so 2 hertz, okay. And then it says we are at a position of x is equal to 5 centimeters. So x is equal to 5 centimeters. So again, immediately, I'm not even going to mess around. I'm just going to go ahead and make that 0.05 meters and get that out of the way so I don't forget. Then it says the velocity is negative 30 centimeters per second in the x direction. So remember, velocity is a vector, so that negative sign just tells you it's moving to the left instead of the right. That's all it tells you. It's 30 centimeters per second. So I'm just going to immediately make that negative 0.3 meters per second and have that already done. Okay, so now I've got all that done. And it tells me to find the period first. Okay, so A is where I want to find the period. So the period, if you remember, there's a relationship between period and frequency. So period is just 1 over the frequency. So that one's pretty easy because they've given us the frequency here. So that's just 1 over 2 hertz. Now remember, hertz really is number of oscillations per second. So the units on it are number per second. So number is just a number. It doesn't have any units. So remember, that's per second. So when I divide by it, that's going to flip the seconds up to the top and make that 0.5 seconds. Okay, so that one's pretty easy. We like those kind because those are pretty easy. Okay, then the next part is a little more involved because the next part wants me to find the amplitude. Okay, the amplitude. Now the amplitude is going to take a little bit more effort because I'm going to have to use conservation of energy to find the amplitude. Okay, so for the next part, I want to find A. Now, A doesn't come out of frequency. It doesn't come out necessarily of X. We could write the equation of motion if we wanted to and try to figure that out. But the problem is I don't know where this thing started, if it started at an amplitude or if it started at 0. So the easiest way to do this, even though it takes several steps, is to use conservation of energy. Okay, so I want to ultimately use conservation of energy. So if I write down what that says that energy is equal to kinetic plus potential, which we've already seen before. So I know that the total energy is 1/2 Ka squared, and there's the thing that I'm looking for, so that's a good sign, plus 1/2 mv squared, or equals 1/2 mv squared plus 1/2 kx squared. So all I've done is I've substituted in for energy. This is kinetic energy, and then this is potential energy. So total energy equals kinetic plus potential. This is plain old kinetic energy like you saw in Physics 1. This is spring potential energy. Okay, this is the thing I'm looking for. So I'm feeling pretty good about life because I kind of recognize all this stuff. The only problem is that they did not tell me what K was in the problem. Okay, they didn't tell me what K was. All right, but they told me enough to find K. So first, I need to solve for K, little k, spring constant. Okay, I need that to be able to do this problem because I've got mass and I've got the position and I've got the velocity. So the only thing I don't have in here besides the thing I'm trying to solve for is K. So I need to figure that out. But it's a block and spring system. Okay, it's a block and spring system. And if you remember, for a block and spring, okay, there is the angular frequency of that system, omega, is the square root of K over M. And they have told me enough that I can solve for K using that. Okay, so remember, this is a thing called angular frequency. It relates to the angular velocity from Physics 1. So angular frequency. But the angular frequency is related to the regular frequency. If you've read your chapter and looked at your notes, the angular frequency is just 2 pi times the regular frequency, and I know what that is. Okay, so it's just 2 pi times the regular frequency, so that's just 2 pi times 2 hertz, because they told me what the regular frequency was. Okay, all right. Again, I'm not going to get overly zealous about putting stuff together. I mean, you can, and that's okay, but I'm just going to leave it like this for the moment. Then I'm going to go right here, and I'm going to rearrange this and solve for K. So I'm going to square both sides and solve for K. So I get K is equal to M times omega squared. I know what M is. They told me in the problem. It's 0.2 kilograms. And I know what omega is. So I can square that. So that's going to be 4 pi squared times 4, and then like that. Okay, so I just squared this thing right here. Okay, so 4 pi squared, and then the 2 hertz is 4. And I can put all that together, and that's fine. All right, so that gives me K. And you can put that together as a number because you've got a calculator and you can do that. But now what I can do, once I know what that is, and I think when I worked it out, I ended up with like 10.05. So when you work it out, this is 19 continued, or no, 25 continued. Okay, when I worked it out, I think I got K is equal to 10.05. And the units on K are newtons per meter. It takes that many newtons to stretch the spring 1 meter. You can go through it and convince yourself that those units are true, but that's what they are. Okay, so I know what that is. So now I can go back to my equation that I had right here for A. I can go back into here and I can plug in what I've got. Okay, so I'll write that down one more time so we don't wonder where that came from. So it's 1/2 Ka squared is equal to 1/2 mv squared plus 1/2 kx squared. Okay, all right. So now I know all this stuff. So I've got 1/2. I know K is 10.05 newtons per meter. A is what I'm looking for, and that's equal to 1/2. I know what M is. They told me in the problem it's 0.2. I know what V is. It's negative 0.3, but I'm going to square that, so that negative is going to go away anyway, plus, I'm going to run out of room because my Sharpie writes too big, 10.05 newtons per meter, and then X was 0.05 meters squared. Okay, so that's kind of sloppy, but I had to jump down because I wrote too big. All right, so now I just got to do some math. Well, I'm lazy, so I'm going to cancel all these 1/2s out. All right, that helps me a little bit. So that ends me up with 10.05 newtons per meter times A squared is equal to, if I multiply this out, 0.3 squared, negative 0.3 squared is going to be 0.09, and then times 0.2, but I'll let y'all do that with your calculator. I'm just going to go ahead and write it out like that, because when you square it, it's going to be that, plus, still not managing my paper space very well, because, you know, pandemic. So all you got is a bunch of math now. You just got to multiply these numbers out, solve for A. So when I did that, I hope I did it right. I got A is equal to 0.066 meters, or 6.6 centimeters if you want to write it in centimeters. Okay. All right. So the only new part that's here is using, the only physics 2 part that's here is using this. It's using this concept of what the angular frequency is for a block and spring system, and using that to solve for K, and then put that back into the energy conservation problem. Okay. All right. So no cats. I don't want you. Go on. All right. There is a C part to this. C part says, what is the maximum speed? The maximum speed is pretty easy compared to what we just did. It's a much shorter process, okay? So the maximum speed just says that I'm going the fastest when I've converted all my energy, all my total energy into kinetic energy. So my maximum speed is going to be when the total energy is equal to K max, and I don't have any potential energy because I've gone to zero. So that happens at the equilibrium position. All right, so 1/2 Ka squared is equal to 1/2 mv squared. I know everything in there except V now. I've solved for K, I've solved for A. I know what M is, so I can solve for V. Okay, so if I plug in my numbers, I've got, well, I can go get rid of that because I'm lazy. So I've got 10.05 newtons per meter times 0.066 meters squared. And that's equal to my mass, which I forgot because it was 900 years ago when we started this problem, 0.2 kilograms times V squared. And you're going to solve for V. And when I solved for V, if I did my math right, I got V max is equal to 1.82 meters per second. I hope I did my math right. So you just solve for V from there. So that was a lot easier than what we just did. All right, any questions about that part?
Can you go back to part B? Why did you substitute the angular velocity constant in?
I didn't substitute it in. I used it to solve for K. All right. I needed to find K to be able to use energy. So I used it to solve for K. All right. So get pulled out here. So I needed to find K to be able to use this equation right here because it shows up here, and I can't cancel it because it doesn't show up here. All right. So the only way I've got to find K, because it's not a given piece of information, is to use the angular frequency. All right. And since it's a block and spring, I know the expression for the angular frequency of a block and spring is this. And that's got the thing I'm looking for in it, is K. All right. All right. And then I know that I've got enough information. I know what omega is. It's related to the regular frequency, which they gave me. And then they gave me the mass. So I was able to rearrange this and solve for K. So I didn't substitute it in. I used it kind of as a separate piece over to the side to solve for K. Does that help?
Professor Burris, I have a question.
Mm-hmm.
Okay, for K is equals to mw squared, why was only the 4 pi squared and not the whole thing squared?
Well, because you mean why it didn't I put 4 squared here, or why didn't I square this?
Like this 4 here, the 4 on this side, the second 4, how come that whole thing wasn't squared instead?
Because 2 squared is 4, so I already did that part.
Oh, okay.
Yeah, that's why. Okay. That's why.
Thank you.
I already did that part, so yeah, that's why. Okay, any other questions? And I don't square the m because it was under the square root sign. So when I square this, it just gets rid of that square root. Okay, so the m is not squared because it was hiding under the square root sign. Okay, any other questions? That help? That answer y'all's questions? I think I had 2 different people asking there. So that
Yes, ma'am.
Okay, good. All right, so the last part, we're still working on this same problem 25. We're almost done though, I promise. Okay. The last part says, what is the total energy? And that's probably the easiest part of all. So this is still 25. The easiest part, it says, D says, what is the total energy? And that's just 1/2 Ka squared. And now we know both of those things. So we just plug in. So it's 1/2 times 10.05 newtons per meter. And then A, which was, I forgot, 0.066 meters. And you square that. And I don't think I actually worked that one out. But you can do that pretty quickly with your math. Okay, so you just multiply all that out, and that gives you the total energy in joules. Okay, so you can work that out, and it's going to be something, because I don't have my calculator handy, it's going to be something in joules, but you just multiply all those out. Now, only this part is squared, not these guys, okay? Only the A is squared on that one, all right? Okay, any questions on that part? All right, we're going to move on then. And let's see, I think the next one that I wanted to look at was problem 30. Okay, problem 30 says the free fall acceleration on the moon is 1.62 meters per second squared. What is the length of a pendulum whose period on the moon matches the period of a 2-meter long pendulum on the Earth? Okay, all right, so 30. So I know that G on the moon is 1.62 meters per second squared. Okay. And I remember from physics 1, if I don't remember anything else, I bet I remember that G of the Earth is 9.8 meters per second squared. Now, some classes you might have used 9.81. If 0.01 makes a difference to my world, then I'm in trouble, so I'm just going to use 9.8. All right. I want to find the length of the pendulum on the moon that will have the same period as a length on the Earth of 2 meters. Okay. Now, I know that the equation for the period of a pendulum, if you read your chapter or looked it up, is the square 2 pi times the square root of L over G, where L is the length and then G is the acceleration due to gravity of wherever you are. Okay. All right. And I know that they've given me enough right here that I could solve for the period and then come over here and substitute, but I'm going to be lazy. I'm going to say I want T on the moon to equal T on the Earth, because that's what we want, right? We want the periods to be the same. Okay, so I can write those down. So I know the period is going to be 2 pi times the square root of the length on the moon over G on the moon, and I want that to equal 2 pi times the square root of the length on the Earth over G on the Earth, right? Because that's the equation for period. And then I'm happy because that cancels. Okay, and then I can square both sides and just get length on the moon over G on the moon is equal to length on the Earth over G on the Earth. And then I think I know everything in there except length on the moon. I know the length on the Earth is 2. I know G on the Earth is 9.8. And I know G on the moon is 1.62. So now all I got to do is cross multiply and do some algebra. All right. And I got length on the moon when I solved it to be equal to 0.349 meters when I solved it. So now, can you do this the other way? Can you take this number right here and this number and plug it in here and find the period and then go, okay, I want that to be equal to what it is on the moon, and do, yeah, you can do that, but this is just the same. It's the same difference. Okay, I know I want the periods to be equal and some stuff cancels and my life is easy. So it's less steps if I just say, oh, I want the periods to be equal. So let me set them equal and see what happens. Okay, so this equation right here is for a simple pendulum. Okay, if you read in your chapter, they tell you the equation for a block and spring, and they tell you the equations for a simple pendulum. Those are our 2 simple harmonic oscillator systems we're going to look at in this book or in this class. So writing those down is, or knowing what those are, is pretty useful. Okay, any questions about this one?
I got a question.
Okay.
All right, so on this specific question, couldn't you just cross multiply without doing the pendulum?
No,
Doing the equation?
not necessarily, because you have to know that these are linearly related. Sometimes you'll have a problem where they're not. Sometimes you'll have a problem where there might be a squared underneath here or something, depending on the system you're looking at. So you have to set the periods equal, and then in this case they happen to be just linearly related. So if you get in the habit of just cross multiplying, you're going to think that works every time, and it doesn't. Okay, in this case that would happen to work, but that would only be for this particular problem. So I don't like to say, oh, I can just do that, because then I think I can do that on every problem that has to do with period, and that's not true. Okay.
Yes, thank you.
Okay. All right. So yeah, I don't like to take those kind of shortcuts simply because it lulls me into a false sense of security thinking those shortcuts work every time, and then I get in trouble later on. Okay. All right. Any other questions about that? Okay. I want to talk just a little bit about some things that you're going to see in the next lab and also in chapter 15. I want to talk a little bit about some different systems we're going to look at. So if you've gone through the notes, you've seen these already, but I just want to briefly talk about how we came up with the equations. So when we look at an equation, when we look at a system such as a tube opened at both ends, so this would be something like if you took a straw and you blew over the top of it and you made it whistle, but it's open at both ends. So the air columns are able to move, or some musical instruments or tubes open at both ends, or like a guitar string. It's not open at both ends, but it's fixed at both ends. So it's still symmetric. It still has the same boundary conditions at either end. So a tube open at both ends would have antinodes at both ends, but a string fixed at both ends would still be symmetric. It would just have nodes at both ends. It would have stopped motion at both ends, okay? So I want to show you how we come up with the equation that we have in the notes just quickly so that you are convinced that I'm not lying to you. So when I have a node or an antinode at both ends, what that does is that gives me whole numbers of what are called standing waveforms. And I call them footballs because they kind of look like footballs when you draw them. But I want to start with the simplest standing waveform that I can support on a symmetric waveform. So in this case, I've got no antinodes at both ends. If it were a string fixed at both ends, what I would have would be something that I would have something that looked like that, where I had a node at both ends, okay? But it's still the same shape. It's still one whole football, okay? It's just I've cut this one in half and flipped it around. All right, so we call this the fundamental frequency. The lowest frequency standing waveform that a system can support is called the fundamental. All right. It's also sometimes called the first harmonic. All right. So I've got a tube of length L here. Okay. And I've got one standing waveform. So I want to know what the wavelength of this waveform is. So I need to know how many lengths of this tube do I need to traverse to trace out this whole football. So that's what these dotted lines are here. If I want to trace out this whole football, I've got to go one length of the tube to get that part, and then I've got to go one length of the tube to get that part. So the wavelength of this waveform to trace out the whole thing is I would have to traverse 2 lengths of my tube, or 2 lengths of my string. Okay, so that's my wavelength. But then I remember the wave speed equation says V, the wave speed, is the frequency times the wavelength. So if I rearrange that and solve for frequency, that's just speed over wavelength. So I'm just going to write that down and say, okay, I know what the wavelength is now. It's 2 times the length of the tube or the string. Okay, so I've got one waveform, so that's why I've got the 1 here, and I've got V over 2L. All right, now, but I can have what are called harmonics. The next simplest waveform, I still have to have a symmetric boundary condition. So I still have to have a node or an antinode. So for a string fixed at both ends, this waveform would look like this, where it would be fixed at both ends like that. So 2 footballs, there's 2 footballs here. Okay, there's a half on each end and plus 1 in the middle. All right. So if I want to trace out a whole football, I have to travel 1 length of the string. So the wavelength for this waveform for 2 footballs is just the length of the string or the air tube. So I'm going to write that V over 2 or V over L. Now I did a little math trick here because you'll see in a minute why I did this. 2 over 2 is equal to 1. So I'm just going to put 2 over 2 here, and you'll see why I did that in just a second. So 1 length of the string, V over L, and that's 2 over 2. Okay, I just put that in there because I felt like it and because I'm going to need it in a minute. Now, for the third harmonic, and my drawing is terrible, but hopefully you can see what's going on. Each one of these footballs takes up a third of the tube. So 1/3, and these two halves would take up 1/3. Okay, so now my wavelength to trace out a whole football, okay, to trace out a whole waveform would be 2/3 the length. So 1/3, 2/3 to get a whole oscillation. So 2/3 L. So V over 2/3 L, but then fractions say the bottom of the bottom goes to the top. So the denominator of the denominator goes to the numerator. So that's 3V over 2L. Can you see why I did that there? 2V, 3V. Okay, so I got a reason for putting that 2 in there. So 3V over 2L there. I'm going to do one more just to see if there really is a pattern. And there is. Okay, the next one is 4 footballs. Again, my picture is atrocious, but hopefully you can figure out what's going on. Each one of these footballs takes up a fourth. So 1/4, 2/4 to trace out a full wavelength. Now you say, but Dr. Burris, that's a half. It is, but I want to leave it alone, and you'll see why. So that's going to be V over 2/4 L, and then I flip the bottom of the top, so I get 4V over 2L. So I've got a pattern, right? I've got a pattern. I've got V over 2L for the first one, so I could magically put a 1 there. So 1V over 2L, 2V over 2L, 3V over 2L, 4V over 2L. There is a pattern here. The pattern is whatever number of footballs I have, it's that number of footballs times V over 2L. So like here I had 4 footballs, so it's 4 times V over 2L. So there's a pattern. N is 1, 2, 3, 4, whatever, how many ever footballs I have. So it's just the number of footballs times V over 2L. Or if I remember this is the fundamental, I can replace that with the number of footballs times the fundamental frequency. So here's the trick. When I have a system and I set the fundamental frequency of that system, then all the harmonics are set. You can't have, like, say, for example, the fundamental is 100 hertz. Then my next harmonic would be 200, and then 300, and 400, and 500. It has to be whole number multiples of the fundamental. I can't have 132 or 150 because those are not whole number multiples of my fundamental frequency for 100. So when I set my fundamental frequency for my string or my tube, I set what harmonics I can hear. All right. Does that make sense to everybody, kind of, sort of? Yes? Okay. Silence is considered yes. Well, sometimes, though, I have a situation where I have a tube that's asymmetric. I have a tube closed at one end. So like a brass instrument where you blow into a mouthpiece and it comes out a bell. So now, instead of having a symmetric system, I have asymmetric. So I'm going to kind of do the same thing, except here it looks a little weird because I've always got this half of a football. So to trace the first one out, I actually have to imagine extending this out. So I go 1 length, 2 lengths, 3 lengths, 4 lengths. So the wavelength of the first one is 4 times the length of the tube. So there's my frequency. Now it turns out that because you've got this half of a football, because you've got this asymmetry, you're going to skip your even numbered harmonics because you can never have whole numbers of footballs. So the next simplest pattern I can have with an asymmetry where I have a node at one end and an antinode at the other is 1.5 footballs. And then each half takes up a third. So the wavelength here is 1/3, 2/3, 3/3, 4/3. So 4/3. And again, put that on the bottom. Flip your bottom of your bottom to the top, so it's 3V over 4L. Same thing for 5. Your next simplest one is 2.5. If you look at the drawing and you satisfy yourself, the wavelength here will be 4/5 L. So each one of these is a fifth. So F5 is 5V over L. So there's a pattern here too, or 5V over 4L, excuse me. So there's 1V over 4L, 3V over 4L, 5V over 4L. So there's another pattern. And the pattern here is for this waveform, it's the number of harmonic you're on times V over 4L, but M skips the even numbers. It's 1, 3, 5, 7. But there's still the relationship between the number of the harmonic and the fundamental. So again, once you set the fundamental, you set all the harmonics for that system. Okay? All right. Any questions about that? So that'll tie into what we're going to see in the chapter on sound and talking about standing waves. Okay? When we talk about standing waves and sound and different musical instruments and stuff like that. Okay? All right. So let me get out of this real quick. And let's see, does anyone have any questions about anything that we talked about today? No? Okay, I'm going to stop the recording.